Okay, so quickly, oh, interesting. That's very interesting. Okay, perfect. So how many of you think that the second exam is harder than the first exam? How many of you think the second exam is easier than the first exam? Okay, then we succeeded. Most of you, I would say more than half of you turned it in about 15 minutes or earlier than the original end time. So I think we timed it right. The first exam was a little longer and I was a little surprised about the length. So, but we have been paying attention to that. Today, we're going to talk about two things. One is how you're going to be able to extend your knowledge that you learned from ECE 408 into other types of programming interfaces. But also, many of you, when you begin to apply your CUDA skills to real applications, many of these applications will have cluster-level parallel execution. So this is a quick introduction about how the CUDA kind of programming environment fit into a cluster-level parallel execution pattern. Okay, so that's going to essentially bridge you into the sort of the application world. So we're going to get you to become familiar with CUDA MPI and how we can introduce CUDA code into an MPI system. And you need to first understand the key sections of an MPI application. And this is a great opportunity for me to do a quick comparison about what seemingly to be very different programming systems, CUDA, MPI. But then once you look at it, I would say in a more systematic way, you will see that these programming interfaces are essentially the same thing. And so I want to introduce some of the communication mechanisms in the distributed computing applications and help you to generalize ECE 408 concepts to other parallel programming APIs or application programming interfaces. This is one of the biggest GPU clusters in the world, and Blue Waters Computing System, 2 miles away from here. And it has very impressive specification. For example, it has the interconnect has a more than 1 terabyte per second bandwidth for applications to exchange data, and we see that we have a huge amount of disk drives and storages and so on in the system. So this is what we call the data-intensive application platform. And if we go deeper into this, we actually have 2 similar systems out there based there's a sister system called Titan in Oak Ridge National Labs. The Blue Water system is a National Science Foundation system. It serves most of the what we call the open science teams, and then Oak Ridge system is a Department of Energy system. It's under the control of Department of Energy, and it's allocated in a very different way to the science teams that are doing work of interest to the Department of Energy. And one of the things that striking fact is that these two have exactly the same vendors. And, but we decided to design the system in very different ways. In the Blue Water system has a lower peak performance. So the Blue Water system has about the 11.1. In fact, this is now 13. So it has been enhanced because of the additional GPU capability. So it's about 13 petaflops. And for those of you who are not really familiar with these numbers, meg is 10 to the 12, and gig is 10 to the meg is 10 to the 6, gig is 10 to the 9th, tera is 10 to the 12th, and peta is 10 to the 15th. Okay, so these are the 333s, right? And so this is the reason why October 15th is a kind of an interesting date because it's 10 to the 15th, and it's called the peta scale computing day. Okay, so for those of you who like these kind of little thing, trivias. So the Oak Ridge machine has about twice the peak performance. And the reason why they have so much more performance is because the Oak Ridge machine consists of a whole lot more GPUs than Blue Waters. Blue Waters machine has 7.1 petaflops from the CPUs, and only about 6 gigaflops, not 4, has to be updated. And then Oak Ridge only has 2.6 petaflops from the CPUs and 24.5 petaflops from the GPUs. And if you look at the number of chips, this is actually a very, very telling story. And this is a fundamental reason why all the top supercomputers in the world today use GPUs. If you look at the NCSA, the Blue Waters machine, we have 48,000 CPU chips, okay, in the machine. And the majority of the Blue Water nodes are dual CPU nodes, okay? And then we have about, this is the reason where I really should update this slide, but you're going to see that in the next couple of slides. We have about 4,000 GPU nodes in the system. Whereas if you look at Oak Ridge, they only have about 18,000 CPU chips and have exactly the identical number of GPUs in the system. So every node in that system is a CPU, GPU combined node in that system. So even though they have much, much fewer nodes, right? There are only 18,000 nodes. Each node has a CPU and GPU versus 50,000 nodes in the Blue Waters, and only about 4,000 or so of those nodes are CPU, GPU nodes. The rest are CPU, CPU nodes. But if you look at the peak performance of these machines, you see that you can get a whole lot higher peak performance for some of the applications if you know how to program GPUs. This is the reason why the industry has been going so fast into GPUs, because the amount of compute power they can put together, given a limited number of nodes, is so much higher, and energy efficiency becomes so much higher if you can get your applications to work. Question? Yeah, so the question is how do we interpret this peak performance? The peak performance here is theoretical. So this is just calculated based on the peak of the chips and so on. Then if you really want to know the performance comparison, it's usually about 5 times for most of the big applications. Okay, so this is kind of how the system looks like. It's what we call the torus network. It's a 3-dimensional torus. That is, all the nodes are connected to the neighbors, okay, the immediate neighbors, and then you have a wraparound link to make sure that you don't have to, if you are at one end and the other end, you don't have to go all the way through the machine before you can get to the other end. You can do a little quick hop. So this is what we call a 3D torus. It's 23 by 24 by 24, interconnect, and then so this is the wraparound link. And then all the disk IOs are actually distributed throughout the system, because we need to have so much data traffic in the system, we cannot afford to have a separate file system that feed data into the system. The data has to be embedded in the system to sustain a high enough bandwidth. Remember that PCIe lecture? This is a PCIe kind of thing in the steroid. Okay, you have these essentially what we call the InfiniBand interconnects that take all that data into the nodes. So application-wise, these are the kind of this is a snapshot of the type of application that we run on the system, and you can see that there's a number of these dense applications that use dense matrix. So this is matrix multiplication, right? And similar computation, LU decomposition kind of things. But if you look at all the matrices, by far, a lot more of the applications are using sparse matrices. And because this is a supercomputer, and it's processing very, very large models, very, very large physics, phenomena. And these things, once you start to have very large models, they tend to be sparse. The real world, remember that lecture? The real world tend to be sparse. And therefore, if you look at the real applications, many of them are using sparse matrices, okay? And this is the fundamental reason why 2 years ago we moved some of the sparse matrix material into 408, because many students told us that they actually ended up using programming and maintaining some of the sparse matrix computation when they graduated. And then we have the structured grids, and this structured grid is actually very similar to the convolution that we look at. But all these other things will require additional techniques that we cover in 508 to be able, for you to be able to to master and program. So this is one of the GPU nodes in the system, and this is what we call the Cray XK7 node, and it has one AMD Interlagos x86 CPU chip and one NVIDIA Kepler chip. This system was built 5 years ago. Okay, so this is 3 generations ago. Okay, in terms of our industry. So we are at the point where we're actually in the process of putting together the next big machine. So to replace all the hardware in Blue Waters. So if you look at the interesting comparisons, the peak performance floating point execution rate is 156 gigaflops, double precision for AMD CPU. And then for the Kepler GPU is 1.3 teraflops. So this is about 8 times, okay, about 8 times more, 8 to 9 times more, peak performance. However, the memory bandwidth is only about 5 times. It's from 51 gigabytes per second to 250 gigabytes per second. For those of you who are familiar with Pascal and Volta, NVIDIA adopted a new technology called high bandwidth memory, HBM. And this is exactly the reason why they did it. Because traditionally the GPUs have more than 8 times of the peak, but only about 5 times more the memory bandwidth. But with HBM, they were able to boost it one more time, one-time boost, so that the memory bandwidth ratio against the CPUs is also now more in line with the peak performance. If you cannot match your peak compute throughput with a good peak memory bandwidth, at some point you will be limited by how fast you can get the data into your chips, right? So some of the exam questions are designed exactly that way. There are certain limiting factors. And if you have these limiting factors, it will determine how quickly you can do the computation. So if we abstract this away, you can look at all the top supercomputers in the world today, and a lot of the data center computers at Google and Facebook and so on with GPUs, they all kind of look like this. Okay, so you have these nodes, each node will have so many CPUs and so many GPUs, and these nodes are connected with PCIe. Okay, so that's why we gave that lecture about the GPUs as part of the PC architecture. PCIe is the industry standard for connecting all these components today, and so we can have from 1 to M, 1 to M CPUs and 1 to N GPUs in the system. So then we have these nodes. These nodes are interconnected typically through InfiniBand interconnect. But for most of the data centers, they are connected by 100 the 10 gig Ethernet and going into 100 gig Ethernet interconnect today. So when you program these systems, you're going to have a large number of these nodes. So there needs to be some kind of programming abstraction to represent these nodes and control how these nodes work with each other, communicate with each other. And what you learn in CUDA is actually a programming interface that abstracted the GPU hardware, right? The threads, the thread blocks, and the shared memory and so on. These are the abstractions of the hardware that you're trying to program. So for clusters, you have something very similar. You have these nodes, and you have the CPUs and GPUs, and you have the local memory in these nodes. So these things are abstracted into these nodes, and there will be processes that run on these nodes. So each process compute a part of the output, and these processes will communicate with each other, and we call these processes MPI ranks. Okay, so some of you probably have already heard this term multiple times, especially if you have taken some other parallel programming classes. And also, these processes need to be able to synchronize with each other. They need to be able to make sure that when they try to do something, processes on the other side are paying attention, or before they can move on to the next big task, everyone has finished with the previous task. Does that sound familiar? Like the scan and so on, right? We have to make sure that everyone has finished the previous step before we move on to the next step. So MPI has exactly the same things. Okay, they're just being used in slightly different ways. So let's start by talking about how you can launch an MPI application. So you go into a system that supports MPI, and typically what we call the head node. And in the head node behaves just like a host for the GPUs. And then you can launch the MPI job by running MPI run, and you can specify the number of processors that you want, the number of nodes that you want to have to run your application. And this is a wish, okay? This is a request. Whether or not the system gives you that many depends on whether the system has that resource. So after you enter the application, the system will tell you how many processors you actually got, or how many nodes you actually got out of your request. And you also have an X. Essentially, this X number is the request that you want, and then you need to check whether you have really received that many processes in the system. And then once you get into your application, you need to run a function called MPI init. So this is just a constructor or the initializer for MPI. It just initializes all the data structures in the system. And in CUDA, basically when you include the CUDA runtime does this automatically. And then you have MPI com rank and MPI com size. These are the functions that an application calls in order to figure out, essentially its thread index and also the thread dimension, the block dimensions. Okay, so in CUDA, these are built-in variables that you can rely on in the kernels. But MPI is not a specialized language. It's actually what we call the set of API functions. So basically, all these applications can call these functions to figure out the thread index equivalent and the block dim equivalent things that the system has assigned to these to the threads and the applications. So there is an important constant called MPI com world, and this essentially tells all these communication mechanisms that the scope of the communication is all the MPI processes and nodes assigned to this particular application. So whenever you use this in the MPI com parameter, if you use this constant in there, that means that you are trying to reach out to all the nodes and all the nodes assigned to the application. Okay. Any questions? So this is what we call a API. The API, application programming interface, is what the language designer, MPI language designer, provided to the users. so that the users can call these functions to get the system working, to get the information. And the CUDA API took advantage of the fact that the CUDA in itself is a language. Therefore, you can add all these variables and so on, so that you don't need to go and call these functions. On the other hand, MPI is more a library. So that's why the users need to explicitly call these functions to be able to get that information. Okay? So let's start with vector addition. If we want to do a MPI vector addition, essentially we're going to take a big vector and we're going to divide the vector up into chunks, and then we're going to assign each chunk into to the MPI nodes, and then each node is going to calculate a section of A plus a section of B and generate a section of C. So if you think about it, it's not that different from partitioning the vectors into these thread blocks, right? And then each thread block is going to take a chunk. So remember when we got into the kernel, we have the calculation of how many the index, the mapping of the thread index and block index into the data index. We talk about each thread block will take care of so many elements, so therefore you need to skip over so many when you have a particular block. So that's exactly the equivalent that we're going to see here, where there's going to be the main application. When you come into the main application, every node in the system is going to be running this main program. Okay, so everyone is basically running the same code. So you're essentially already in that kernel, okay, when the MPI application started. So then every node is going to be executing this MPI init to get all the environments set up for the for these nodes. So there's not exactly a host code in MPI that prepares the memory allocation and so on, and then transfer data to the GPU. In this case, you have a pool of nodes or processors in the system, in that cluster, allocated to you. And then everyone is going to execute this main program. And it's almost like you're entering that the kernel for CUDA, and then all the thread blocks and all the threads will be executing that kernel code. So MPI is exactly the same as CUDA when it comes to the fundamental execution model. Is what we call the single program, multiple data, or multiple threads. Basically, all the threads in CUDA are executing that kernel code, right? And all the MPI ranks or MPI processes are also executing the same main program. Okay, so when you come into the program, everyone will initialize its local MPI environment, and then you would call the MPI com rank and MPI com size to figure out the total number of processes involved in this application, and for each process, what is the rank? What is the ID for the process? So a unique ID will be returned to each MPI rank, so that they all have a unique, is the equivalent of thread index or block index. Okay, MPI does not have the two-level organization, so that's why CUDA has block index and thread index, but MPI only has a rank. Okay, now here we start to specialize. Remember, in CUDA there's a host. The host is doing the I/O, and the host is feeding data into the GPU, right? But here you have a whole bunch of these, nodes. So you need to figure out who gets to do the I/O and feed data to the rest. So a very typical pattern is that the MPI, there will be one or a small number of nodes or processes that will be designated as the data servers, and they will be doing the I/O. Remember when I showed that, show the Blue Waters picture, I showed that there's some red dots in the system that are doing the file I/O. So whatever nodes running those, nodes that have those localized disks will most likely be running as the data server, okay, for the rest of the, the compute nodes. So here it checks how many, MPI processes were allocated to this application. If there are less than 3 for this application, essentially we say, oh, we need to have 3 or more processes. If the, if the allocated number of processes is less than that, then the application doesn't have enough resource to run. And this usually has to do with the memory requirement. Usually when, when people scale MPI, there are 2 main concerns. One is your data going to be able to fit into the collective memory of all the MPI nodes? Because a lot of these data are so big that they don't fit into one individual node. So you may have terabytes of data that you need to process, and then you only have maybe 16 gig or 32 gig of RAM in each node. So in order to fit all that data into the, into the RAM, you need to have so many nodes that collectively you have enough DRAM to be able to hold all the data so that you don't end up with all these terrible paging behavior when you do the application. And the other one is you also want to make sure that you have enough compute power to crunch through the data. So you employ more, more processors to be able to, collectively have enough throughput to process the data. So it's very typical to test whether whether the count size is greater than is at least a certain amount, so that you can say, okay, I will have enough memory to be able to hold the data, and I will be able to make enough progress with all the processors I have. So here we show the example of specializing the MPI processes into compute nodes and data nodes. So basically, the first from 0 to process ID minus 2 will be the compute node, and the highest ranked, the MPI rank process will become the data server. So it's the largest number. But this is arbitrary. This is just whatever the application wants to do, as long as you do it consistently within your application, you know which MPI ranks are the data servers and which MPI ranks correspond to the compute. And that's when you need to use for all the communications. And finally, once these things finish, you come out, you do an MPI finalize. So this means that you're shutting down the system. Okay, this is equivalent to exiting CUDA, and then you return. In CUDA, we have shared memory communication. We have a global memory. So all the threads can access a global memory. MPI is not a shared memory, global memory type of application programming system. It's a distributed memory system. So all the MPI processes will have their own private memory. Okay, so you cannot expect to access a single global memory for your data. So every process can only access its own data, but if it needs to have data from other MPI processes, there needs to be explicit message, send and receive message. This is actually the reason why MPI is called MPI. MPI is what? Message passing interface, right? So it's fundamentally a message passing programming model. So the first important API in the MPI MPI environment is MPI send. You send message to someone else, and so you have all these parameters. The starting address of your send buffer, and you have the number of elements in the send buffer. This is actually one thing interesting about MPI. MPI messages are not sized according to bytes. The MPI messages are sized according to elements. So that's why you need to have message types. So this is the data type that you need to specify, and you can have 4-byte integers and 8-byte integers, and you can have double precision floating points, single precision floating points, and so on. And in CUDA, when we copy data from host to device, remember we only provide the number of bytes so that they don't have to provide that second parameter to tell you the data type, right? So these are the trade-offs that people make in these programming systems. The problem with this approach is that porting MPI to different systems is actually tricky, because if you have try to port MPI from one architecture to another architecture, if you have some differences in terms of the word size and double precision, single precision, then you can actually create some difficulty in terms of the implementation of these message passing parsing functions. So the destination is the rank of the destination, essentially the address, okay, the process ID of the process that I'm trying to send a message to. So there's a destination address or rank of the destination, and then you have a message tag, essentially as a little metadata, and then you have the communicator. So the communicator essentially tells you, which group will be involved in the send receive. How many MPI processes will be involved? Typically, we just use the world. Okay, so that essentially all the processes involved in this application will be should be listening to the send. So we have essentially all the nodes, all the processes that want to send data can execute the send simultaneously. And then hopefully you will have all these other processes that are supposed to receive the data will be listening. So that's why they need to be executing a function called MPI receive. So this is the counterpart of MPI send. And you provide the buffer so that you can actually have the data written into the buffer for your usage. And then you'll say, what's the maximum number of elements I expect to receive from the buffer, and what's the data type, and who am I expecting the message from, okay? And then you have the com and so on, the status, because you need to check the status and see if you have indeed received the data correctly. So you have, so all these nodes that receive data need to execute the MCI receive. So here is a quick vector addition code. Okay, yes?
The send and receive has to be triggered at the same time.
No, so the question is whether or not the send receive need to be triggered at the same time. No, they will wait for each other. However, you want them to be roughly at the same time, because if someone sends a piece of data, but then the receiver doesn't show up anytime soon, then your application will have a long waiting time, right? And then so chances are that will mess up your resource utilization. That someone will be waiting, doing nothing. Okay, so here, in fact, we're going to see some of that in the example. So let's say we already have this, the vector addition example. So this is the function that the data server will be calling. Remember, after we did this initialization, then each process is going to execute this piece of code. So 0, let's say if we have 4 processes involved, 0 through 2 will be the compute node, and 3 will be the data server node, according to this piece of code. So 3 of them will be calling this compute node function, and 1 of them will be calling this data server function. And this is actually the equivalent of control divergence in MPI. Okay, this is when the threads or processes will begin to to do different things. If you don't do this kind of if then else kind of statement, then all the MPI ranks will be executing the same code. They will be executing the same thing. Okay, so this is the equivalent of control divergence. Now, so when we when the data server calls the data server function, this is when the data server MPI rank will be specialized to do data services. Okay, so within that process, we're going to be doing some kind of I/O, and then doing some so this essentially we'll figure out how many processes set the communication size for the for sending the message to the compute, and then we're going to allocate memory for the input A, input B, and then so normally we'll do the file I/O, but here we just randomly initialize A and B. So this data server is doing the I/O that reading both A and B, the entire vector. And in reality, this may not happen, by the way. Remember, in a MPI application, one of the biggest reasons why I just said that we use MPI is because we need to have the collective DRAM to be able to hold all that data. So if we assume that one of the nodes can hold all that data and then distribute the data, it's kind of, it defeats the purpose. So that's why, we usually will have a large number of data server nodes anyway in the system, and also the data will not be reading all at the same time. The data will be actually reading in chunks, and then the chunks will be shipped to the different compute nodes using something similar to the CUDA stream, right? When you think about CUDA stream, what we did was we divided the data into chunks, and then we will have the CUDA main copy compute and CUDA main copy for each chunk. So that will be exactly the type of pattern you would expect for MPI applications that use process very large amount of data. So they will have these chunks, and then each chunk will be shipped to these compute nodes as soon as they arrive from the disk I/O. So then we're going to initialize the pointer to the input A and pointer to the input B, and then we're going into this loop. This loop is the MPI, is the loop of the data server that will be distributing data into the compute nodes. So it will iterate from, actually this should be 0 to the last compute node. So this code is actually should be, is inconsistent with the other node. So I'm going to need to go and correct this. And then for each iteration, you're going to be sending a chunk of A and chunk of B, a chunk of A and a chunk of B to one of the compute nodes, identified by that node process ID. Okay, so you do this iteration, and then you distribute all these data into the target MPI processes. So these are the MPI send functions called, function calls in the data server. So you would expect that by the time we get to the compute node code, there should be MPI receive in that node, in the code, right? So after we finish sending all the data out, the data server is going to wait until the compute nodes finish their work. So this is done with MPI barrier. So basically, everyone involved in this group, this communication group, have to eventually call this function so that everyone arrives at the barrier before they can continue. Okay, so the server is going to be to call this function, and it's going to be waiting at the barrier until all the other, all the compute nodes come back. So then, after the barrier, if the data server comes out of the barrier, that means that all the compute nodes have already checked in, have already shipped the data, checked in and say, I'm ready to give you the data. So then the MPI, the data server will go through the loop to receive all the data from the compute nodes. So this is going back to your question earlier. So we could just go ahead and have the data server to go and wait for all the compute nodes. But it's better if the server actually go and do some other things, and then do a barrier synchronization and say, I'm not going to, to begin to do the receive until I know that the compute servers are ready, right, to send back the data. So this is the MPI. So I'm going to go through a loop and call the MPI receive function once for every compute node, so that it will match up with the compute node send, the functions in the from the compute node from the compute nodes, and then you would. So this is where you collect all that data into the output vector, and then you store the output vector, and then you free up the memory. If we look at the compute node, these are the nodes that will receive data from the data server, do the computation, and send the output back to the data server. So we have, we need to have local memory allocation, and in CUDA, this is already done on the host, right? The host code does all these memory allocation. But remember, MPI does not have the host code. So every node has to be able to, to allocate memory for themselves. So this is the allocation of the section of the section, and then you would get the input data from the server process. So you would receive MPI receive A, MPI receive B, and this is to receive the section that's shipped to you from the data server. So the data end goes through that loop, and they call the send A, send B section for every compute node. So you just iterate through it. Whereas on the compute node, everyone just do a receive A section, receive B section, but there are multiple compute nodes, right? So that then the number of sends and receives will match up. So you can, at this point, you can do a vector addition. You can loop through the section, okay? Loop through the sections and do the addition. Or at this point, you could offload the data to the GPU. You could send that data to the GPU with, like with all the CUDA main copy and CUDA kernel launch and so on. So you can either do the compute, and this we already know how to do, right? We already taught vector addition in CUDA. So this is exactly the vector addition, code that you learn in the MP. And then after you're done, you report to the barrier. Okay, you say that I'm done. Okay, I'm done with compute. I'm ready to send the data. So I'm reporting to the barrier. So when all the compute nodes report to that barrier, that means that everyone has done the computation. They're all ready to send that data, right? They're all ready to send data. And that's when the data server also will be exiting the barrier. Remember, everyone has to go to the barrier, and then they all leave the barrier. Yes? Oh, yes. That's an excellent question. That's actually a few lectures. But let me kind of point to, when you take a class from Bill Grob or Sanjay Kalei, those are the kind of questions. So they're going to love me for this. So basically, most of the machines are connected through these, mesh-oriented connection or the torus kind of interconnect. What that means is that each node is only going to be connected with 6 neighbors. Okay, 2 up, 2 from back, and 2 left right. Only 6 neighbors. So if you want to communicate from this node to something that is farther away, you have to go through other nodes. So that's why some of the messages could be going through other ranks. Okay, and that affects the latency. It also affects the bandwidth that you have available. So they're what we call the data affinity assignment, okay, of MPI ranks for exactly that reason. But
they actually go through like kind of a terminal nodes and allocate memory out of the nodes and transfer again.
in the message implementation, it actually some of these nodes will serve as the network, essentially the network hubs that will just forward the message from one node to another node. Exactly right. Okay. By the way, we're extremely lucky on this campus that we have, Bill Gropp, who is the lead person for the MPitch implementation of MPI, and he's someone who's known in the world about his MPI work, and he teaches the MPI type of class. So you should either take it from him or you take it from Sanjay Kalei, who's the who's the lead person of Charm++, and he intimately knows about a lot of these implementation details. Okay, so compute, and so you tell the you tell the host you tell the data server that you're done with the compute. So all these servers, all these compute nodes essentially report back to the barrier and say, okay, we're ready to to send a message. So then everyone comes out, everyone will do an MPI send, and then the host, the data server will be doing that loop of MPI receives. So then they will all match up, and they will all, so the data server will be grabbing the data from each of these MPI sends from the compute node, and then they will complete. They will all complete, so the compute node will free up the memory, and then the data server will do the write into the I/O and then finish. So this is a very naive, very simple piece of code for MPI. The biggest part that I want you to remember, parts that I want you to remember is these things are not that different. If you think about the conceptual model, all this MPI rank code are essentially equivalent to the kernel code in CUDA. And because the MPI processes need to be able to do some of the memory allocation and so on, so there's no host code, right? Because there's no host code in MPI, so all these processes need to be able to have do more work and I/O and so on. So they tend to be more capable, than the CUDA threads. And because MPI is a library, it's not a language. So in order for these MPI processes to be able to know what is my process ID, you need to do a function call. Whereas CUDA has the built-in variables that give you that information because the implementation is a language. CUDA is a language. There's a compiler that set up these things for you, and hardware supports that for you. So, and then, we still have exactly the barriers. The barriers are there to organize the activities in time so that before you do, like say, MPI send receive, you know that people are roughly at the same place, so they're going to be able to pay attention to each other in the data communication. Any questions? And one of the things that, if you really understand this, then the next slide should make perfect sense. So this is, essentially where the most important trend in GPU cluster computing today. It's what we call a GPU direct. And basically, what we talked about was that at the MPI, the data, let's say the data server and the compute server are sending and receiving data, right? So if you look at that compute node, there's something that is a little bit of inefficient because the MPI, the compute node, is going to receive data from the data server. So that receive is actually going to go through a network interface card and copy the message into the node level memory, and then it's going to do a CUDA main copy from the node memory into the GPU memory, right? So you have these two hops of data copies, In fact, one of the headaches in the early GPU cluster systems is that MPI requires pin memory as well. Okay, when you receive a piece of data or you send a piece of data, if the data in your memory is not in a pin allocation, then you need to copy that the message data first into a pin buffer, and then you need to copy that pin buffer into the the real user level buffer. If you try to use DMA between your network interface and your system memory, your node memory. So for exactly the same reason that we talk about in the CUDA memory, sort of the CUDA memory transfers. So there's a concept called MPI pin memory. Okay, you can allocate your application data in your MPI application as a pin allocation for that reason. Okay, unfortunately, the MPI pin memory and the CUDA pin memory were not compatible with each other. You cannot allocate a pin memory for both MPI and CUDA. So that's why in the early systems, when you use a GPU with MPI, you need to do a message receive, copy into so that will be received into an MPI pin memory. And then you need to copy from the MPI pin memory into the CUDA pin memory, and then you call the CUDA main copy async from the CUDA pin memory to the CUDA GPU memory, and that was bad. So that got fixed, after a couple of years. But then, people say, wait a minute, if I just want to make sure that my data goes from I/O into my GPU memory, why do I need to do all these intermediate, node memory, transfers, right? So why doesn't the network interface card just do a DMA into the CUDA, into the GPU memory? Why do you need to do these intermediate hops? So this is called GPU Direct. The Mellanox, the manufacturer of InfiniBand Mellanox, was the first manufacturer that enabled this capability. Essentially, when you use a InfiniBand network interface card, it will recognize the GPU memory, okay, the GPU memory as part of the system physical memory, and it allows the user code to tell it, the MPI code to tell it to just directly deposit the received message into the GPU memory. Okay, so that's as simple as that. It actually takes a huge amount of technical development and the change in the driver code and in the way that you bring up these devices in a PCIe environment to be able to enable that. Okay, so this trend is continuing, and now there's a concept called RDMA, so remote data, direct memory access. So what that means is that instead of calling a driver code is to send a message from one node to another node, you can actually, your application can refer to the memory of another node. And the system implementation will allow you to be able to directly copy a piece of data from a remote node's GPU memory into your GPU memory. That's called RDMA. And you can do this without going through the MPI interface. So you don't have to send receive a message. You can just go and say, I want to grab a piece of data from your memory. And the network interface card from Mellanox will help you to do that today. Okay, so I saw a question.
Yeah, so I was going to ask, does that mix C1 taking address space with CPU address space?
Okay, that's a very, very good question. My honest answer is, I actually don't know. And the reason is, I can think of multiple ways that they implemented. The early implementation is actually separate physical address space. However, after the Pascal generation, they have enough support for the unified memory, and it's really enough now that I can imagine that they would do that, but I don't know whether they actually did it. Okay, you can probably test it and find out if you're interested. Any other questions? Very good. So this is what I wanted to talk about in terms of MPI. You know what? That little circle here is what we call the RDMA support. So you can now copy. Interesting. There's some missing arcs. So imagine. Oh yeah. Okay, it showed up. It has a little bit latency. So you can actually, directly go from a device memory, GPU device memory, through the network interface cards and then deposit into that without going through the MPI software layers. Okay, so that's what RDMA is about. Now, so we're done with this, and I want to just kind of, quickly summarize a few things, and then we do the course evaluation. So we started by talking about CUDA. Okay, and so we introduced a few things that you absolutely should take from this class. The first one is we started with this whole memory model, and if you go and try to understand any kind of parallel system, the first thing you need to understand is exactly how do we organize the threads and how we organize the memory with the threads. Okay, so in CUDA we have two-level organization: thread blocks and threads, and all these threads can have common access to a global memory. MPI does not. Okay, and then all the threads in a thread block can have access to a shared memory, right? And that shared memory is much faster than the global memory, but only the threads in the same thread block can share the contents, right? And if you load a piece of data into shared memory, it will be loaded multiple times, once per thread block, right? And we actually had the exam question about that. And then every thread has private registers. So that's the CUDA memory model. And that's the CUDA threading model, right? Here, when you learn a new programming interface like MPI, the MPI threading model is the MPI processes. And everyone has an MPI rank, and you need to call these functions to get your MPI rank, and then they don't have global memory. So in order to exchange data, you need to have something equivalent to CUDA MPI send, MPI receive. So those are the very basic things you need to learn about these programming interfaces. We spend a little bit of time, right? We spend a little bit of time talking about that at the beginning. And then we talk about matrix multiplication, and then we talk about convolution, right? And it turns out that these are probably the most important computation patterns for engineering applications, okay, for most of the engineering applications. So if you really understand matrix multiplication, if you really understand convolution, you will be able to understand all the differential equation solvers, and you will be able to understand all the neural nets and so on, as we know now, right? So then we move on to what we call the collectives: reduction, scans, and these are the ways for us to have multiple of these threads to come together and summarize data, or to be able to contribute to each other's results. So these MPI, which I did not cover, MPI has a collective library. And you will see reduction, you will see sorting, you will see some of the scan, prefix sum in the MPI libraries for exactly that reason. Okay, because they are very important computational patterns when you need to have threads to interact with each other to be able to summarize data and so on. And then we we started to go into less regular data structures. So that sparse matrix is really your kind of an entry point into the real world applications. You start to be able to see how people avoid representing zero elements, and then but how do you what kind of arrangements you need to make in order to maintain some of the regularity, to eliminate some of the control divergence, to be able to avoid some of the data divergence or the improved memory coalescing in CUDA, right? But if you look at the MPI, sparse matrix libraries, you see exactly the same things. Because the sparse matrices in the MPI also have, the data needs to be distributed into different nodes. So, because of the variation, you may have load balancing problems. Some of the nodes may receive the rows that are too small, right? So you have exactly the equivalent of JDS kind of format in order to be able to gauge how many rows, so that you can send different number of rows to different nodes. Because if you have you're in the region where the rows are long, you can send fewer nodes to fewer rows to the nodes. But if you're in the region where each row is short, you can send more rows to a node, so that the net compute load will be balanced, right? So this, and then you also have people like Sanjay Kale, who will be, essentially dedicating their life to this load balancing problem. And in Chunk++, we have this over-decomposition strategy. And then, you will have, they have a dynamic load balancing approach to send more and more of the smaller chunks into the node to balance the load. So these are the kind of things that, even though you learn these things through one programming interface in some form, as long as you understand these concepts, it's very, very easy for you to go into another system and look at it and say, oh, yeah, so they're trying to solve very similar problems, but it's a different context, so this is the reason why they had to do things this way, right? So, it really is not about learning every possible programming interface. It's impossible to do that. And, a few years from now, there will be another new programming interface. So this is the reason why we designed 408 the way that we designed it. We go into one programming interface deep, but along the way, we introduce all these patterns and concepts so that you really understand the whys, okay, the why these things are there for this programming interface. Because if you only know what, here are some, here's some function, names, and then the how. If you want to do this this particular algorithm, you can call these functions this way, or you can do that. That will make you a valuable engineer for a few years, okay? If you know why these functions are, there, if you know why the functions are designed these ways, then you will be able to be a good, valuable engineer for life, because new problems come up, new systems come up, you know exactly how these things need to be redesigned. And when the new system comes out, you will understand how the differences really come about, so that in your mind, you can sort through these things really, really systematically. So that's the summary I wanted to make. From now until the end of the semester, it's really about applying everything you learned to your project. Okay, I'm not joking. So you really need to to spend the time to work through these optimizations. We're already beginning to see some some posting on Piazza and say, I tried this thing and then it didn't improve performance. What do I do? The answer is you haven't spent enough time. Okay, you haven't spent enough time looking at the profile data. You haven't spent enough time understanding what's blocking you, but those are the kind of things that will eventually make the whole thing come together for you, and so that when you go to a industry job, when you go to grad school, you're not going to be an idiot. Okay, you're going to be able to do something And then if it doesn't work, you don't have to go back to your advisor right away and say, it doesn't work, what to do next. Your advisor will look at you and say, where did you come from? And if they ask you that question, don't ever mention my class, okay, if it comes to that point. But ideally, all of you will be able to, to do the work, do the analysis, and evaluate and figure out what's wrong, and then do the improvements so that when you go to the meetings with your advisor, with your boss, you'll say, oh, I did this, it didn't work out very well, and the manager was waiting to say you're an idiot, and then you say, but I did this analysis and I figured out that here, the bottleneck is here, I changed that, look how beautiful the results are. And then your raise, your stock options, and your thesis will all come with it, okay? So that's when you mention, by the way, I took my parallel programming class with Professor Wenmei Hu, okay? So that's when you mention ECE 408, CS483, and my name, okay? So that's it. So on Tuesday, Carl Pearson is going to be here, and that's going to be our last project town hall meeting. But it doesn't mean that that's the end of the help. The TAs are still going to be holding these office hours, and that you're going to need some of those hours. You're going to need to go and discuss your situation and then show them the profile results and so on, so that they could help you to be able to diagnose and then to be able to, to do the next level, okay? So take advantage of the office hours. But next Tuesday, Carl is going to come here and he's going to, to actually go through a few more things that we expect to see, right? And how we expect he's also going to show you a few good examples of good reports. Okay, the reports that got really high scores in the past and why we give them, good scores. And that's another, feedback that the previous students gave us. They would like to see some examples of good reports. So that's the reason why we're putting together that Tuesday. Okay, so now it's the end. So I need to have someone to help with the course evaluation. And I need to have a volunteer who's going to collect. Great. So I'm going to give you the envelope. And let's pass out the forms. By the way, until the exam, I didn't believe that I actually have so many students in my class. But that's the benefit of modern technology. As long as you keep up with the coursework, I don't care. You're watching as long as, but make sure that you really are keeping up with the class, okay? Okay, very, very good. So if you have extra, just put them, don't fill out extras, okay? Leave them blank and put them into the envelope. Yes. I don't. However, Carl will have an extra office hour next week. I'm traveling next week. So can I borrow your pencil? I don't want them to send it to me. Do you know how to drop this off into?
Yeah, in the EC building in the
there's a blue
mailbox thing.
Yeah. So or send me an email so that. Okay.